Good morning, ladies and gentlemen. My name is Martin Rees. I'm an astronomer from Cambridge, and it's my pleasure and privilege to chair this session this morning. But before that, I'm supposed to do two things. First, to remind everyone to turn off your mobile phones, and secondly, to remind you that there are emergency exits, one there and two at the back. Well, this morning's speaker is Professor Brian Schmidt from Australia, and he's famous in the astronomy community for his work in one of the most important discoveries of recent decades in astronomy, indeed in physics, discovering that the universe is accelerating in its expansion, which tells us something basic. It tells us that empty space isn't just nothingness, it's something which has a sort of tension or pressure in it and has a complicated structure which will be a long time before we understand. So he's been involved in a really important discovery. And his role was to lead one of the teams that made this discovery, which shows he's a great organizer as well as a great scientist. And he's gone on, after having successfully organized 20 astronomers, to be the Vice-Chancellor of the Australian National University, where he has to organize, I guess, several thousand people. And he is wonderfully suited to that because, as you'll hear now, he's not only a great scientist, but he's a great communicator. And so it's my great pleasure to invite him to speak to us this morning. And his title is Big Science, New Collaborations and Engagement with Society, the SKA, the Square Kilometre Array, as a 21st century exemplar. So I invite you to welcome Brian Schmidt to give his lecture.
Thank you, Martin. Thank you, everyone, for coming out for the first session after the party, which is always a bit of a challenge. I did see a few of you there. I have to admit I haven't felt that old in a long time. I didn't see most of you there, though, including Martin. I'm hoping you won't have to use the emergency exits as part of today's festivities. But I want to talk about what is an exciting project amongst many exciting projects. But this one is a project that has some differences. And I think it's worthwhile thinking about those differences because they provide both opportunity and they provide challenges. And these challenges we need to understand because in life, we don't just do what's easy if we want to make progress. We actually need to do what is right. And I think the Square Kilometre Array is a great project that is not easy, but it is right. So let's talk, if I can figure this out, as I show you an image of the radio sky. That is an image of what the radio sky looks like from one of our observatories down the Murchison Wide Field Array in Australia. The radio sky is, in some senses, maybe not as exciting as the optical sky, but that's probably because we simply do not have yet as advanced instruments. And if you can look in the detail that we're used to with, for example, the Hubble Space Telescope, there is a whole world that I'll tell you about out there to be explored. So one of the things that is important about astronomy is it has brought humanity together since our first times looking as a new species on the planet. This is one of the oldest things we have, a record of humanity, the Cave of Lascaux. And you can see Pleiades, the seven sisters as it's known, shown as 6 stars as it always is, because that's what it looks like to the human eye, right next to the shoulder of a bull, which is interesting right where it is in the sky, next to Taurus the bull, making you realize constellations are more than 17,000 years old. The stories behind constellations are more than 17,000 years old. What else do we have as humanity where we can show a story that's that old? And it's more interesting than that, because Pleiades, the seven sisters, has its own story, for example, within Australian culture. The Aboriginals talk about the seven sisters. This is really going to get old. this is what the Pleiades look like in a telescope, the Seven Sisters. But that's, of course, the same story that we tell in Europe. Yet the Aboriginals have been separated from Europe by 40,000 years. Same story, Seven Sisters, 6 stars, 1 missing. Quite remarkable. And you see that story repeated in India and Thailand, various other things. It's not universal, but it is a story that seems to go back through the millennia. So, astronomy is something that we all share. Every human has seen basically the same set of stars that we see today. And it is a place where science itself emerged. If you think about how science got it started, it really started with the very precise measurements of Kepler going through and working with the motions of planets based on Greeks going through and thinking through that. Galileo then coming through and saying, here's some observations. Newton then bringing together a mathematical framework. And that sort of is the scientific revolution started with astronomy. And it is still today a place where we work together. One of my colleagues said one of the great things about astronomy is the data is vast, but it has almost no inherent worth. And so it's really easy to work with. No one's fighting over IP issues on the stars. Although if you try to name one after yourself, you will get a nasty gram from the International Astronomical Union, of which I'm a card-carrying member. All right. The other thing I want to emphasize, and this may cause a little bit of controversy, is that we do fundamental science, and science in general, because it is interesting. But our governments pay for it, the amount they do, because it's useful. And I think we need to remember that. And it doesn't mean that this is more important than that, but it means we need to consider that when we tell our stories to the world, because I truly believe it is useful. And we demonstrate in all our daily uses of everything from the World Wide Web to digital cameras, the use of these fundamental bits of physics, astronomy that we do. So let's talk about telescopes. Most people have a good idea what an optical telescope is. Of course, we have 2 of those each in our head, our eyes, our little telescopes. And they see radio telescopes. But we don't really think, what's the difference between these things? I think it's worthwhile reflecting, to probably use a poor turn of phrase, on the differences. So we have, for example, one of the first big telescopes here south of England, Herschel's 40-footer. We have Jodrell Bank just down the road, still one of the world's largest radio telescopes. We have one of the most expensive facilities in the world, ALMA, a collection of astronomers from Japan, the United States, Canada, and Europe, putting that together. We have the this is the Westerbork, which is what we call an interferometer. We have the Hubble Space Telescope. And these things work at different frequencies of light. And so if you think at a very fundamental what a telescope is, it is a device that takes light and focuses it such that the paths of light are all exactly the same length. That's what allows you to make an image. Okay? And the mirror is constructed in the shape of a parabola, typically, because that geometry gives you that perfect focusing. And whether or not it's a radio telescope, where you can use chicken wire as your mirror, or optical telescope, where you can use, you have to use something like a lens or a reflecting mirror to do it, it's the same basic idea. But there's a problem. Light is a wave. It's also a photon, and we'll talk about that in a second. And so that you actually get interference patterns, which we call diffraction, based on the wave nature. And you can go through and then derive from the equations of waves that how sharp you can focus depends on the wavelength of the light and the diameter of the mirror. And so you can't do any better. And that gives you the angular size as we measure. So in how big, for example, a degree on the sky or a tenth of a degree, or we normally measure it in arc seconds, which is 1/3600th of a degree. So that is what you're physically limited by quantum mechanics, or the fact that light is a wave, is what you can achieve. And so when you're working, for example, with optical light and the Hubble Space Telescope, you have a 2.4 meter telescope, and you're looking at light that has a wavelength of 1/2 micron. So, 0.5 times 10 to the minus 6 of a meter. Whereas the radio telescope, you're seeing light that has a wavelength of 20 centimeters. That's 400,000 times bigger than optical. So if you're going to make a radio telescope that sees the same resolution as an optical telescope, you're going to have to make it 400,000 times larger, and that means a diameter of 1,000 kilometers. So that's one of the reasons radio telescopes typically have not provided the sharp pictures of Hubble, is they got to be the scale of the Earth. Now, we can actually start making them the scale of the Earth with some complications. So, the other thing we need to realize is that if you have light, light is a wave, but it is a particle. And in an optical regime, we detect things as particles. Within the radio, we detect things as waves. They're energy. And so to show you the basic idea, here is an experiment where you put light through 2 slits, and then you detect the individual photons. And although each individual photon kind of randomly lands, they form a pattern. And that is that wave pattern of interference, where these photons can end up or not end up. And you see preferentially photons here act as a wave. Optical, we measure the individual dots. In radio, we measure the energy in the waves. Because the photons have so little energy, you literally cannot detect them. But the good news is there's a lot of them, so you can add up their combined effect in the form of their energy. So that is a fundamental difference of how an optical telescope works compared to a radio telescope. And so, for example, if you put a big optical telescope, for example, on the Subaru, you have a detector, in this case, almost 900 million pixels, a big mosaic, and so you get to take a little image of where every photon lands. In radio telescopes, we don't have big imagers like this. Rather, we typically have, in the case of Jodrell Bank, a single little antenna that measures a voltage, 1. So I can kind of go, it's about that bright, it's about that bright. So it's 1 little pixel at a time. So another reason why with these big telescopes you have a difference is that you literally don't get to take 900 million little bits at a time. You have to do it 1 little piece at a time. Well, that's not completely true. We can be clever. And clever is by just going through and making, for example, the first multi-pixel detectors, for example, what we've done here in Australia, something called the multi-beam receiver. Or you can be even more clever and use something that we call interferometry, something that won a Nobel Prize just down the road from here. And so, for example, the Ryle array, before it was disbanded, you sit here and you make a bigger telescope out of a bunch of little ones. And so what you can do is you can use the fact that radio waves are voltages, and they're only going at a billion cycles per second or thereabout, and you can actually use electronics to change the distance between the telescopes. Rather than having to make a giant parabola out of steel, you can use electronics to sort of put in that same geometric shape into how the light gets all into a focus at once. Furthermore, you can do other things where you measure the interference pattern between each pair of telescopes. And with mathematics, you can then construct, it turns out, an image using this. And you get an interesting feature, is that this acts as a telescope with the diameter of how far apart the telescopes are. So you've got to do a lot of electronics, a lot of calculations. And if you go through and look at this interference pattern, as the Earth rotates by, then the sky changes and you can keep measuring that interference pattern, how it changes, and mathematically construct a model of what the sky looks like. And we can do this across the whole Earth and even go into putting objects, radio telescopes, into space. And that allows us to make huge telescopes with very large diameter, and despite being radio waves, our best images that humanity has created are actually at radio wavelengths because we've been able to make the telescopes so big. And one of the most advanced facilities we have, for example, right now is the VLA in New Mexico. There are 27 antennae, and so you look at how many patterns, how many combinations. You've got, well, this one has 26, 25, 24, 23. You end up with 351 sets of interference that you can calculate. That's a lot of calculations, it turns out. So it's actually quite challenging to do, especially 25 years ago. But it allows you to make quite exquisite images. And so, for example, this image of a nearby galaxy, which we'll talk about later, has two jets shooting out. And we'll talk a little bit about why those jets might be there in just a second. But you can also see there's still some patterns here. And if you didn't have just 27 antennae, but you had 1,000, well, that would be great. The problem is instead of having 351 calculations, you're going to have 1,000 times 999 divided by 2 calculations to make. That's a lot more. So you need to have a lot more computer time to do it. The good news is the advancement of technology is now providing the opportunity to build a huge radio telescope because Moore's law has provided us huge advances in computational power since the VLA was made in the late 70s, early 80s. So, the advantage that we have in radio telescopes, this is the next generation 39-meter optical telescope, as I said, is we can put the telescopes on the ground and we can make up for the structure here. So this telescope, very expensive, because you've got to have all of those mirrors lined up so that each piece of light from the sky travels exactly the same distance. Remember, that's a half a millionth of a meter, half a micron. So you've got to do about 10 times better than that. That means it's really thing 40 meters across lined up to, to nanometers. That's expensive. Radio telescope, I take each bit, plop it around, get the computer out, and say, yeah, it's about that far, and put it in. You can actually calculate it once you get the data in, and you can get around this problem. You can just literally add telescopes as the technology increases. So it's a beautiful process that we can. And so we believe we are in a position over my lifetime to scale up a radio telescope that grows with technologies to about 1 kilometer squared in area. And to give you a sense, radio frequency is roughly 1 gigahertz. That's a frequency. And if you think about what the processor in your iPhone is, it's about 1 gigahertz, which means technology is such you can do the calculations on these quite well. We don't really have good ways of doing calculations with photons yet. We're working on that. That's a technology that's emerging. It's not there yet. Maybe someday we'll be able to play the same game with optical telescopes, but we're not there yet. We're a fair ways away, I'm afraid. So what do we see in optical? Well, we like optical. Our eyes, as I said, are optical telescopes because we live near a sun. Sun is hot. The sun glows because it's hot. And so optical really tends to see things that are hot. So for example, when we look out into the sky with the Hubble Space Telescope, we see places where stars are forming and places that are dark is where there's dust, it's absorbing the light. And then you have literally the dust and gas, which is heated up, and the gas will essentially emit light like a neon sign because it's hot from the stars, and the stars themselves glow again because they're hot like the sun. And so we see things, as I said, stars that are forming. We see stars that are dying, like this one. we see collections of billions upon billions of stars, galaxies. So there's several 100 billion stars here glowing. So optical telescopes really see us in that hot part of the universe. But that's not the only part of the universe. If you look through, radio allows you to see cold gas. But it also allows you to see really fast-moving electrons, things that are either really, really hot or often in funny situations where there, whatever reasons, electrons have been made to move very quickly. So if you think about cold gas, hydrogen, turns out, has a proton and electron, and those have quantum mechanical spin. And if the spin gets misaligned, that's a small energy change, and you get a photon out. A photon that is at 1.4 gigahertz, 21 centimeters. And there's a lot of hydrogen in the universe. It's the most prevalent thing there is in the universe by a factor of 3 over helium. And so each one of these photons is very faint, but there's so many of it, it's a way to go through and look at the universe in gas. The other thing is that if you do, or I should say, and this is what nearby galaxies look like in hydrogen, cold hydrogen gas. And you can see often they have little holes in their center because there's a lot of stuff going on there, and the hydrogen is ionized, so it's not emitting there. And this gas is where stars form out of. It's the reservoir of all the fun activity in a galaxy. You run out of this gas, then you're really on a course to death as a galaxy. You're just sort of fading, you're fading out to oblivion once you run out of your gas. Now, if you look at an electron that, for example, encounters a magnetic field as it moves, it spirals in that magnetic field, and as you accelerate it in that spiral motion, you get photons that come out. That's called synchrotron radiation. That, depending on how fast the electron's moving, will often come out, a lot of it, in radio wavelengths. And so wherever you see electrons moving through magnetic fields, the universe is full of magnetic fields, whenever you have electrons moving quickly, you're going to see these synchrotron radiation. And so in images like this, which turns out to be, we believe, a supermassive black hole shooting gas out at nearly relativistic speeds, there's electrons there, they encounter magnetic fields, they spiral, they put out synchrotron radiation. But you also see it more close to home, for example, a supernova remnant. This is Tycho Brahe's supernova remnant that he saw in 1572, now seen 400 years later. And what happens here is there's a blast wave of material going out, lots of electrons there. And as it crashes through the galaxy's, the small amount of gas that's there, remembering space is not a pure vacuum, you create shocks, and that stirs up the electrons and makes magnetic fields. And so you see synchrotron radiation coming out of the blast wave of this supernova remnant. These can be almost invisible at optical wavelengths because it's not really hot. There's no material that's heated up particularly. It's just things moving quickly. So it's a different situation. You can see that if you see optical and radio, you get to see most of the universe. There are a few things you still can't see. You need X-rays, gamma rays, but you see most of the universe between optical and radio. All right, so here's a galaxy, our Milky Way, that if you look at with your eyes, and then if you look at that same area in the radio, you see cold gas. You also see lots of little dots if we were to look at synchrotron radiation. But the Milky Way, again, is a galaxy that's still forming stars. And you can see, for example, if you come to Australia, you'll see the large and small Magellanic Clouds compared to looking at the galaxy Andromeda here in the northern hemisphere, which you kind of squint and you always convince yourself that you saw it. The large and small Magellanic Cloud from a dark side are quite obvious, and you can actually, in the large Magellanic Cloud, literally see it's a spiral. And one of the interesting things there is there's a lot of action going on in that part of the sky. Those two galaxies are sharing gas, lots of stars being formed, and the Milky Way is still forming stars. You can see all this gas that's there. And we'll be able to form stars for probably many, many billions of years because we have a good reservoir. although the Andromeda galaxy is going to come in and do a dance with us, and that will really use up, and it'll create a lot of stars, probably 3 or 4 billion years in the future, and that will use up a lot of the gas very quickly when that happens. I probably won't be around here to watch. But if you are able to go through in the galaxy and make a map with radio, you can see beautiful features, the interstellar medium with supernova remnants, new stars, and there's a rich universe of gas interacting with the stars to be seen. But as again, because radio telescopes are still quite small, you typically don't have the sensitivity and the resolution to make these beautiful images. We need to remind ourselves that as much as we love stars, there's still about 90% of matter in the universe is in the form of gas. And so there's a lot there that we're missing. All right. Now, the universe is expanding, and normally I would tell you about 20 minutes about the universe expanding, but take for granted that it is. Now let's run the universe in reverse. What happens? We go back in time, and things are closer and closer and closer back in time, and you get to the time of the Big Bang. When you squeeze things, the universe has a temperature right now, it's hotter in the past. It's more dense. And then there's this time of the Big Bang. So I always say I have no idea what the Big Bang is, I only know what came after. But we do have a very good picture of what came after, thanks to something called the cosmic microwave background. And it's this image made by Planck, the ESA satellite. It's an image 380,000 years after the Big Bang. We look at the sky, it's very clear that the sky at that point is 75% hydrogen, 25% helium. We see sound waves left over from the Big Bang that have been moving around for the 380,000 years, and the universe at this time is 3,000 degrees Kelvin. So it's hot. There are no stars, and there are no galaxies, and these ripples are really only 1 part in 100,000. So we've really turned up the gain so you can see them. And these little ripples, each one of these little dots, that is about 450 million light years today, containing hundreds of thousands of galaxies. And when we look at the galaxies today, we can actually see these little patterns in the galaxies today. It's very hard. We spend lots and lots of years to see those little bumps. And those bumps actually allow us to help measure distances from the present day back into this epoch. But there are no stars and no galaxies, and then something happens. You know, over time, we go from that to a universe that is full of the galaxies and stars of today. And this intervening period we like to call the Dark Ages. Well, I say that as an optical astronomer because there's nothing very hot. Things are hot here, and then they cool off, so I have nothing left to look at. But if I'm a radio astronomer, then it's not the Dark Ages. It's the glowing age. It's the time when the universe is full of cold hydrogen, which can put out its light in the form of 21 centimeter radiation that can be looked at. And then something bad happens for radio astronomy, is the first stars and galaxies and black holes are born. We don't really know the process particularly well. It's very interesting. And those hot balls of gas heat up the cold hydrogen, ionize it so that it's no longer cold and no longer can emit radio waves through 21 centimeter radiation. But that gives us an opportunity, because just looking at a glowing universe isn't very interesting. It's sort of like looking at a white wall. But when it's changing from being to a white wall to a dark wall, there's a lot of information. And this is known as the epoch of reionization. And we can model it. And so in this area, the black areas are the cold gas, which is going to be emitting in radio waves. And as the first stars and galaxies come up, well, you end up making the universe into Swiss cheese. And how this Swiss cheese developed tells us how the first stars and galaxies form. You can figure out when. We can figure out how they do it in clumps. Do galaxies start out big? There's some mysteries we don't understand. There's these ginormous black holes back at this epoch, We have no idea why they're there. I mean, it's very hard to imagine how they got so big so fast. So if we had a sensitive telescope, radio telescope, think of one about a square kilometer in size, you can go through and look back to this epoch and see the universe evolve over time, where you will literally see the universe come alive in these observations. So that is a movie we think that we can make with the correct telescope over the infancy of its life. The other thing is that when we look back after that with radio telescopes, or so with optical telescopes, for example, the Hubble telescope, we get these amazing images where we're looking back to relatively nearby galaxies and then very, very distant galaxies. So we get to keep looking back in time. The further away we look, the further back in time we see. But optical telescopes, the VLA, our most sensitive instrument, don't provide a lot of information to help. And remember, there's a lot of things going on that we don't see in the optical. But with a square kilometer array, you're going to be able to go through with the sensitivity to really see a universe comparable to the optical. So you can put the optical and radio together to understand how the universe has evolved over time. The universe is full of quite amazing objects. I study supernovae. Supernovae occur when stars greater than about 8 times the mass of our sun run out of their nuclear fuel, and their centers collapse down to about the size of Manchester. So you take something 10 million times more massive than the Earth and collapse it down to the size of Manchester. And that makes things quite exciting. And one of the ways we see these objects, again, another British Nobel Prize, was the detection of pulsars. And we believe pulsars are these neutron stars, these cores of these supernovae, that have strong magnetic fields, and at some point electrons come down onto them and they are able to beam out light, which we can detect at radio waves. These things spin quite quickly, often some of them hundreds of times per second. And because they're so big and they're spinning so quick, they're like giant tops and they're incredibly stable. That is, they're not quite as good as our atomic clocks are right now, but they're not far away. And so they provide amazing tests of physics because you can make such precise measurements. Now, if you look through what is possible to do in the future with a square kilometer array, a huge telescope, the universe, our part of the universe, our Milky Way, is full of pulsars. Because there have been a lot of stars come and go in our lifetimes, and you end up with this huge forest of little clocks. And when you're making measurement, one of the things that you can do is you've got one clock, it's great. You got 10 clocks, it's better. You got 1 million clocks, well, that turns out to be 1,000 times better than you can do with one clock. And so that allows you to go down and make measurements that are well beyond what we can do of, for example, general relativity. General relativity is a theory that we know is not right it's not perfectly right. It doesn't play with quantum mechanics. Yet every place that we have tested it, it gets the right answer just bang on. And so this provides a new way to go through and test other things. For example, we'll start being able to see pulsars right in the center of our galaxy, where there is a 4 million solar mass black hole. That is a place where interesting things can happen. And so these provide potential tests of that black hole, but also of relativity. One of the things that we've also seen this year is the discovery of gravitational waves, inspiraling black holes. Now, what an inspiraling pair of black holes does outside of gravity waves, not completely clear because we don't know how much stuff there is. But if there is stuff around them, then you're going to get electrons moving, and there's a reasonable chance that we might be able to see it at radio wavelengths. We don't know. Square kilometer array is certainly one of the places where because we can look at a large part of the sky at a time, that I think we have one of the best chances of really isolating down where these catastrophic events happen, which we can then better understand. There are lots of possibilities when you are able to measure things well. One of the foundations of physics is measurement. And whenever you measure things more and more precisely, interesting things happen. I can't tell you in advance, but we had a surprise in the last couple years, I hope. As I said, in the form of gravity waves being detected. And it turns out, I should also say, the measurement of the pulsars themselves allows you potentially to see very long wavelength gravity waves from, for example, supermassive black holes coming together. That is made much easier when you have more and more objects to measure. But we also have, as I said, we have the known unknowns and the unknown unknowns. So this event, which I'll explain to you, was detected a little less than 10 years ago, and we call it the Lorimer burst. And I think a lot of people honestly didn't believe it was real. What do I see here? This is a measurement over time at the Parkes telescope and frequency of the radio waves. And you can see this little track that came through. It's only a millisecond wide. And the reason it has this shape is that the universe is full of electrons. And electrons are like, in the same way that water provides an index of refraction for light, well, these electrons provide an index of refraction for radio waves. And it depends on the wavelength. And it turns out that it goes perfectly as this parabola. And you can go through and say, that's a lot of electrons it had to go through. And if we use some sensible version of the universe, that object is billions of light years away. So somehow, we had something, a millisecond in duration, travel billions of light years and was detected accidentally. A millisecond of duration kind of tells you that the area that it happened, because of the speed of light, is a millisecond times the speed of light. That's not very big. That's like, the size of a neutron star. But how on earth would you possibly get that amount of energy? Because remember, there's not a lot of energy in radio waves. And so, okay, there was one. There was a few others that seemed a little funny. There were microwaves being opened that were confusing, producing something similar. However, we have now seen on several telescopes these things. They do exist. And they're very, very frequent. That is, there are a lot of them in the universe. I don't think we completely know what they are yet. I think some people would say they're a souped-up neutron star, because some of them seem to repeat. That is, they don't just do it once, they'll do it more than once. And physics can do some very funny things if you can point things directly at you. You can really focus the light. So I would say this is a known unknown. But imagine a telescope that opens up our sensitivity by many, many orders of magnitude. Who knows what we're going to find? These may allow us to go through and learn fundamental things about physics. It's certainly going to allow us to track electrons in the universe, but it is very, very difficult with a big facility to know what you're going to discover. If you look at all the big, certainly astronomical observatories, they've all set out to do things in advance. And most of them have actually delivered on that, although often someone else got there before them. But they end up delivering things you do not expect. So for example, when I was finishing my PhD, the Hubble Space Telescope was being delivered, the Keck telescopes were being delivered. We used those telescopes to go through and use type 1a supernovae to measure what we thought was going to be cosmic deceleration. That was not in anyone's science plan because it involved knowledge that just wasn't there until about 1992. And then we made this discovery of dark energy. That was a surprise. That happens all the time. And so when you have good instruments to do big ideas, usually the best things are the things you can't predict. And we need to understand that discovery is at the core of science. And I think we often forget that, is that we get very much A to B, and we worry so much about doing what we already know that we forget about the stuff we don't know. And that is where science helps humanity in a way that is different than any other part of society. We work on the unknown. We have to have our eyes open for it. It is the revolutionary ideas that come out of that scientific process that we should cherish. There are other things that we can do, of course. This image was taken in ALMA of a forming planetary system where you can see where the planets have literally carved out gas lanes where they go around. With the square kilometer array, with its amazing imaging capability, one can imagine going through and watching these planetary disks form and literally make movies of the whole process of how planets form from scratch. So gravity brings the dust and gas in. Turns out it's quite complicated then how you might well form planets. I would still say there are some disagreements on the actual specific mechanisms, but the best way to break those disagreements is to actually just look at it and see what happens. And so something like the square kilometer array can have a huge capability in getting the image quality that we need to make these fundamental observations. It can also go through and do some other interesting things. For example, you can go through and start looking at the molecules of life. We already know many molecules, and it turns out ALMA is very good at this as well, but there's some very specific molecules you can look at. For example, glycine. And so you have to have a lot of sensitivity to go through, but looking at amino acids and seeing where they are, imaging where they are in planetary systems, give us a better sense of, for example, how the amino acids that are so prevalent here on Earth got here. Is it comets? How did they form out there? These are, again, fundamental observations that one can think about making. There are things that we know almost nothing about. Cosmic magnetism. The universe is full of magnetic fields. We're not really sure how they got there. And one can go through and map them out in exquisite detail by looking at their effect on background objects. There are some really wild things you can do, as mentioned by Brian Cox in the opening. Square kilometer array phase 1, you can detect an airport radar pointed at you around about 10,000 stars. With the second phase, you'll be able to detect TV transmitters to the nearest 10 stars. Now, I'm guessing there's no television in the nearby 10 stars, but you don't know until you look. Might be surprised. This is actually quite interesting. And certainly one of the interesting things that we're getting to is we're able to detect ourselves. I think Martin and I may agree that it'd be good to detect that someone's there. I'm not sure that we should tell them back that we're here, because if they're like us, I wouldn't want to meet us. There's a lot of science. There's about 9 kilos of science in these volumes. Great read, also great bookends. So there is a huge amount going on in the science around the world. Now, it's a complicated organization, but it's an interesting organization. This is a giant astronomical facility that includes countries developed, such as Australia, Canada, several European countries, but also developing countries like South Africa, China, and India. And trying to create a structure that caters for everyone is a challenge. It's messy. It's been hard. I'm sure I can speak to the Director General in the back. It's not an easy group, but it's important. It's important because the world is changing. And we forget. This is population. It's a 21st century world. The world is made up of the countries that are part of SKA. It is Asia. It's Africa. Europe's still important. We have North America. I'm afraid we in Oceania, well, we like to play along and hopefully don't cause too many problems along the way. Some would disagree. The point being is that science, if we really do believe, as I do, that science is a foundation to prosperity. We have to share the science not just amongst the developed nations, but amongst the developing nations, because they're going to get the same things that we get out of it. They're going to get increases in human capital. They're going to get the spin-off ideas. They're going to get the motivation for young people to go out and have a passion to learn really, really hard things. These are important because I personally would like to make sure that our population tracks on the bottom side of those curves. And the way we're going to do that is through prosperity, because I'm not at all convinced that we can handle 12 billion people on this planet. I'm not even sure we can handle 8 indefinitely, and I know we're going to be there, but the lower we can keep that number, the better. And that means working together and not just handing out ideas, but making the world communally responsible for these ideas. And that is what SKA is about, but it's hard. It is harder than just doing it with your friends. And so that's one of the things that I want to emphasize, is that it is important, but it's going to require patience and time. Now, in order to build a telescope, you have to put together a huge, complex array of engineering and ideas to design. And it's interesting to see how these things come together. So I'm just going to focus on 3 of those projects that we're working on in Australia. And so they involve places from around the world in each area, and they involve industry. The world is changing quite quickly, where industry is having more and more R&D capacity. It's not just fixed in research institutes and universities. And we have to learn to work with these partners because they're not good at everything, but they're really good at some things. And when industry is better than universities at things, they're often hundreds of times better. They're not very good at the long game, coming up with ideas that may or may not be useful. But once there is an idea, boy, they're really good at making it cheap, fast, easy, efficient. And for a project like I've described, we have the big grand ideas, but we also have the need to make it cheap, fast, and efficient. So working with industry, real opportunity here, and a necessity as well. And so the amount of data coming through this project is truly astronomical. And it involves getting the data through fibers. Usually we convert things to voltages, and there's a lot of computation required. But the computation doesn't necessarily just have to be in dedicated facilities. We have opportunities to, again, leverage on industry. But the amount of data, just to give you a sense, is that you get about 100 gigabits per second from each telescope. And there's going to be hundreds of telescopes. And you have to process that probably on site in a dedicated facility. There's clever ways we can do that. But then eventually you do actually need to deal with the data as scientists. And there's where we need to think about things at a scale, which, if I show you CERN, 15 petabytes, that's a big data, we're talking 300 petabytes. Moore's law is actually not completely crazy now. Facebook, you're uploading 180 petabytes worth of high-quality images, movies, posts of your friends each year. So industry has already figured out how to do this. Now, Mark Zuckerberg has $30 billion to do that, and SKA doesn't. But the good news is that we are working with companies like Facebook and Google to deal with these types of data. My own university developed a way of dropping, just through very clever, simple architectures with the operating systems, the energy cost behind this by 25%. And that was just last week. That's a huge, I mean, that's $50 million from a little piece of cleverness from academia. So we're in Facebook's good books right now for that. If you look at this challenge, it requires, as I said, industry. And so just to give you a sense of how you might do things, we're beginning to play around, and a group involving people around the world in the US have gone through and tried to see, well, what about using something like Amazon, which has data and computational services? And you can go through and you just buy the stuff, and for $2,000, you can go through and do a huge amount of data crunching. Now, the problem is most of us are used to not paying anything because there is a $50 million supercomputer that someone else pays for. But SKA doesn't have that luxury. Someone's going to pay for the supercomputer. It's going to be us. And the cost of, for example, disk space, you can go through and you can sort of guess what you think it's going to look like. You can see reality's been different, but the cost has actually gone below the estimate. And so things are looking good this way. You can make things cheaper in a way which is roughly guessable. We talk about what people are going to do on big projects. Martin asked, what are we going to do about all these people, big projects? Well, my experience is that I have to compete with industry right now. I'm producing lots of students that are really good at big data. I had a student who said, I've decided I'm sick of academia. You guys treat me like crap. I've been trying to be as nice as I can, but the reality is academia is hard. And so she said, well, I'm going to go apply. And I said, OK. So the next day she called me and says, I got 3 job offers in 24 hours, making twice to 3 times what she was making as a postdoc with me. I have another student who was off at a startup and was immediately offered, without even a reference from me, a salary more than a professor. The opportunities are huge for people working in this area. Maybe not entirely in academia, but that's okay. If we have the fluidity of people moving in and out of academia, that's one of the things I'm trying to think about in my own university, is how do I allow people to come in and out of industry? Because there's a lot of interesting things going on in parts of industry right now. Then I get the best of both worlds. But that's a cultural change within our institutions we're still working on. There's citizen science. One of my postdocs is leading something known as the Radio Galaxy Zoo. Involves people in Oxford, involves people around Australia, around the world, the US. And they're using people who are just citizens who want to go out and understand the universe and contribute a bit, and they're using them to analyze fairly complex astronomical images. Well, that's fine, but then you get to actually train your neural networks and your deep learning algorithms from what they've learned so you can put it out on scale. So it's useful, because I'm afraid artificial intelligence algorithms are dumb still. They still need human input, and then you sort of reproduce humanity. And we're getting better and better at those, but I would still say this works much, much better. But this has a double use. People are out there getting excited. They're learning about it. They're learning about the whole process of science, probably learning about artificial intelligence algorithms. They're involved. Well, this is a precursor of the square kilometer array. She's talking to IBM South Africa right now, my student in Australia, about how we can scale this up and use it for the Meerkat and for SKA phase 1. Very exciting. Science is diplomacy. We've talked about it, and I just want to give you a case. Radio astronomer Chris Christensen, who made something called the Criss-Cross, one of the early pioneers of radio astronomy, in 1963, for reasons unknown, decided to break down the walls into China and just go there. And he managed to get an invite. He was one of the first Westerners to be into that part of China. And then the Chinese came back and visited Australia in 1964. And when I talk to people, Department of Foreign Affairs and Trade in Australia, they talk about this as being the foundations of Chinese-Australian relations that eventually got our prime minister to be there in '73, after Nixon went in '71 as sort of his own little weird thing, and Nixon was like that. But the point being is science diplomacy is real. I just went with my prime minister to China earlier this year, and about a quarter of the trip was around SKA. It was only 24 hours. But we went and spent 3 hours doing SKA things on this trip. When I talk to South Africans, when I talk to Italians, when I talk to Dutch, I'm with my ministers, and that's what they're talking. Square kilometer array is right in the middle of it. It is, as I said, this thing that we share. It is an excuse to be nice and civil and work constructively together, and it leads to other things. We look at Brexit right now. Science, with its 25-year horizon, will be the thing I think that people will appeal to smooth over what is going to be an uncomfortable time. And we need to make sure that we keep doing that, because the science is important. Everyone loses if we don't do that, and everyone knows that. So science diplomacy is important. And when I talk about sharing science with, for example, developing and developed countries, we're putting in the trust mechanisms of how you get China, India, Europe, Australia, South Africa, all to work together. And when we do that in this space of astronomy, and they realize, oh, this can work, then it can translate into things like banking and commerce and other things. So it is a foundation. We should not shy away from how important that is. Science is also about technology. I said earlier that science is the amount of money that is paid into it is often because of its usefulness. So we do astronomy because it's aesthetically interesting, but along the way we do interesting things. So as part of Australia's pre-SKA work, we have been developing big imaging devices equivalent to digital cameras for radio telescopes. And interestingly enough, our work was spearheaded by John O'Sullivan, the person who invented Wi-Fi. Here is a man who made literally hundreds of millions of dollars from inventing Wi-Fi. And when he finished with that, he said, I'm going to go back and I'm going to become an astronomer, make almost no money, and I'm going to go back to my roots and I'm going to try to do something new. That is the power of astronomy, and I think he is a great example. These objects are amazing. Unfortunately, they're also expensive. Whether or not we're actually able to use them on the first phase of SKA, to be determined. But in inventing these things, I promise you these things are going to be used in other places because they have this amazing capability of going through and allowing us to image like we are used to in the optical in the radio. And so it is the beginning of something, of a technology which I think will have use one way or another, and eventually I think will find itself in radio telescopes around the world. Science is also linked inexorably with culture. If you haven't had a chance, please go to the City Hall Library, which is a beautiful library, and in it is some amazing artwork about what we describe as shared skies. Indigenous artists of both South Africa and Western Australia coming together and expressing within those, their ancestral cultures what astronomy means to them. And so there's remarkable artwork there. It's really great to look at. And those cultural bonds really do flow out into society and help astronomy with that aesthetic aspect of helping us understand our place in the universe. And it is a great way to do something which is extraordinarily unusual. All right, so I've got you excited about SKA. Where are we going to put it? Well, this is a map of radio interference around the world. I'm colorblind, but this color, which I won't describe to you, is where there's no radio interference. Now, it's not easy to build radio telescopes on the ocean, but you can see that North America, South America, Northern Africa, Asia, Europe, you have soiled your radio skies. You've really done them in. If you go down here and here, you see pristine radio skies. And so there's a good reason to think about putting your radio telescopes in those areas because you don't want to be interfered with by everything. And so the SKA consortium has gone through and chosen 2 of these incredibly pristine sites in Western Australia and in South Africa. And we are going through and selecting sites based on essentially population density, so less than 4 people per kilometer squared in Southern Africa. And within Australia, a tiny population of 160 people in an area the size of the Netherlands. So that's a tiny number of people. Not much happens there. The challenge, of course, for this site, it's actually very hard to get there. For me, from Canberra, I have to do a 4.5-hour flight to Perth. I then have to do an hour-and-a-half flight up to Geraldton, and then I have to do a 6-hour drive. And so it's about the same length of time for me in the end as coming to England from Australia. It's a long, hard way to get to. And so these extreme radio quiet zones are unique in the world, and they require protection. There is a huge demand in both countries for radio frequencies. And so you have to be organized, and we have to think long term, and we have to get the people and the country behind protecting the radio quiet zones. We have been building prototypes because we've never built telescopes like this before, and it's important to make sure we know what we're doing when we build a billion-dollar instrument, and we really are going where no person has gone before. So it's easy to screw up. And so here in Europe, for example, we have LOFAR, centered in the Netherlands, but across Northern Europe. And this is a low-frequency telescope that can look at that early time right after the Big Bang where the universe is in the dark ages. We have in China a huge telescope. This is a Google map satellite image. So I think it's no longer true that the only human structure you can see from space is the Great Wall. This is 500 meters across. It was just finished. A huge thing. Makes Arecibo, the big radio telescope, this is another order of magnitude larger. It is an amazing structure that only the Chinese could build. And this will be really interesting as it comes online over the next couple years as a prototype. In Australia, we have a 36-element radio interferometer called ASCAP that has those new fangled, what we call focal plane arrays that can go through and make radio maps, not just 1 pixel at a time, but over many pixels. We have our own version of LOFAR called the Murchison Wide Field Array. And in South Africa, we have just the recently first light commissioning of Meerkat. Maybe? Meerkat, which is down in the Kauri Desert, you can see is something similar to ASCAP, although will be made much larger in the meantime. And then within that South African site, there is also another epoch of reionization called HERA that is being done with the US, UK, Italy, and South Africa. So there's a lot of prototypes. Some might argue too many prototypes, but this is hard work, and it is really going to be important to get it right in the next phase of the project. And so what we can look forward to is not just the telescope technology, but these are remote sites, and so you have to use newfangled technology in the form of power. So hybrid diesel / solar arrays that go through and allow us to deliver power at an affordable price out in the middle of nowhere, knowing that electricity systems generate radio interference. So you have to really be careful in what you do. We also have a headquarters to be here in Manchester and a beautiful building, I'm sure, that will show itself in the not too distant future. And we have these amazing facilities to look forward in the years to come, which I'm hoping we can see here, the Australian facility, which, to give you a view of what it's going to look like, this is the low frequency facility where you have these little groups of antennas spread out, and they're all added together electronically to make a giant telescope, literally not getting close to a square kilometer array in the next 10 years with that facility. If we look on the South African site, we have nearly 200 antennas coming together to form an amazing array that will just have the ability to make images like the Hubble Space Telescope in a way that we just never have been able to do before. And so again, the fly-through movie, these dishes concentrated in the center and then spread out beyond South Africa up into countries across Africa, again providing this remarkable instrument for the future. This is why I normally use Keynote. Anyway, it's a long project. It started in the 1990s. It is continuing today. The UK has put 270 million euros on the table. Australia has put 293 million Australian dollars. There are many other groups ready to put money on the table to do this. That's money over a long period of time. So it's a long-term investment. And we can hope that if we keep on the path, I would say this would be the earliest things can happen, but we can start looking here at really being to use the telescope in the next 5 or 6 years. I'm afraid one has to be patient as an astronomer. And of course, in the more distant future, we have the even larger true square kilometer array, which is 2023 onwards. That's probably a device that I will be able to use in my retirement. But if you don't plan now, remember we can add as we go, it never happens. And so this is a telescope that will move with technology. It's helping developed and developed nations. It's going to work with industry. It intersects with the public. And in the end, as I said, we're all here because we believe science brings great benefits to the world. And if we really do believe this, then we need to take the time and ensure that we share this science with absolutely everyone on the planet, not just our friends. Thank you.